before I end this lecture, I just want to at least present the statement of the theorem that we're going for. So this will be what we look at in the next lecture. And this is sort of the ultimate payoff of all of our hard work so far, is going to be this theorem. It'll probably take a couple of lectures to prove it. So now we're starting with a, not just garbage, but we're starting with an actual algebra of sets, A, and an actually countably additive function on A. Let me use the pointer here. An actual algebra of sets and an actual countably additive function. In other words, a measure, an algebra of sets and a measure. Then this theorem tells us, let me skip to the really interesting part immediately. This is why this is amazing. Mu star, the outer measure induced by mu, is the unique countably additive extension of mu to the collection of mu measurable sets. So this is our holy grail that we've been after, our extension theorem. Now, who cares that we managed to extend to the mu measurable sets? Well, look at part 2. The collection of mu measurable sets is a sigma algebra. And, oh, by the way, the countable additivity is preserved of mu star. So this is a sigma algebra. That means it contains, so this is a sigma algebra and it contains A, right? So that means it contains the sigma algebra generated by A. So we have this next part, part 3. Since A mu contains sigma A, we can also say mu star restricted to sigma A is the unique countably additive extension of mu to sigma A. Actually, I mean, it's not a consequence of that, but this is one of the things we get. We have extended, we now have, through this use of outer measure induced by mu, we have a way of extending a measure on an algebra of sets, which is countably additive, you have to assume it's countably additive, to a countably additive measure on the sigma algebra that algebra of sets generates. So, for example, we could have our algebra of sets be the collection of elementary sets on the unit interval that we've been working with. Then this theorem would allow us to extend that uniquely to mu star, a measure on the Borel sigma algebra on the unit interval. So that's quite an achievement. So when you extend a measure like this to like the unique countably additive measure on these mu measurable sets, this is called a Lebesgue extension. So this is like saying mu star is the unique Lebesgue extension of mu. This is kind of what we're showing here. So one thing I noticed only recently, or I realized only recently about our textbook, is that while I really like the way it's written and the proofs and the way the theorems are presented, sometimes I feel things are a little bit dry. And I think part of the reason is that the theorems don't have titles. So I think at least this theorem should have a title. So since it's about getting the Lebesgue extension of a measure on an algebra of sets, you might call it the Lebesgue extension theorem. But I think then it sounds like Lebesgue proved it. And, well, I'm not sure if Lebesgue proved it or not, but I think it was proven later. At least I find theorems with this as a sort of special case being attributed to Carathéodory. So you might call this Carathéodory's theorem, or Carathéodory's theorem about Lebesgue extensions. Okay, but I'm not so good on the history of these things, so I don't want to make any historical claims. So then, how about we just call this the amazing extension theorem? So this is a hugely powerful result and probably the most important thing we will have proven this quarter in measure theory. So we will not get started with proving this right away next time. There's another lemma that we need, but I just wanted to show it. Partly just in case you wanted to start thinking about your homework over the weekend, since your homework is going to rely on this theorem and its corollary. But what I would really recommend is maybe wait until after the weekend, after those lectures. Then you'll have more of a feel for these things.